So now let's consider the source-free parallel RLC circuit. And you're going to find that the differential equation, although being as a function of voltage instead of current, will have a similar form and similar solutions to what our series circuit had. And also, I'm going to say that although we're looking at the very fundamental differential equation solutions right now, we are going to learn some techniques in future chapters that are going to make this much easier. So, okay. First thing, let me get my pen going back here. Okay, good. So now we're going to consider a parallel circuit. And remember when we did just resistive circuits, if we were doing a series circuit, we tended to write Kirchhoff's voltage law, voltages around the loop. And in a parallel circuit, we tended to write Kirchhoff's current law because we have currents going that have to sum up in a node. So we're going to do KCL because this is a parallel circuit. And basically what we have here is that I in the resistor plus I in the inductor plus I in the capacitor equals 0. So we've written Kirchhoff's current law here. So I in the resistor is V over R. Now the V here is the V that's at that node, but keep in mind that's also V sub C. It's the same thing. So V equals V sub C. And your textbook says that when in this chapter when you see the V, it means V sub C, voltage across the capacitor. So they don't put the subscripts in there. But V sub C equals V, but just for completeness, just to make sure it's clear, I'm going to write it that way. So from Ohm's law, we can get I in the current, I in the resistor just fine. And from our relationships from for a capacitor that we learned, we get I in the capacitor just fine. And then this I in the inductor, this actually comes from the fact that we had this relationship that the voltage in the inductor, which in this case is still V, right, equals L di dt. And so we do a little rearranging of the terms here. L di. And since this circuit has no sources in it, we have initial conditions here and initial conditions here. So we're going to make that come into play in this formula right here. So anyway, we're going to integrate both sides. So from time negative infinity to time negative infinity to time 0, because at time we're looking at what that time has gone on in this circuit for some period of time. It's caused these initial conditions to be here. Perhaps a switch was closed and a source was turned on, and we have some initial energy storage in these devices. And then at time t0, we remove the source and we let the circuit do its natural thing. And so that's why we want to find what the initial conditions are on either the capacitor or the inductor. So that's why we go from time negative infinity to time 0 to find what the initial conditions are. And so this side is easy enough. This is these are easy integrals to perform, but we have some unknowns with it, so let's just do it. And I wrote it wrong here, didn't I? Yeah, it's L. So okay, so we can rearrange just a little bit more right here, and we have 1 over L with the same integral as before. But when we 1 over L negative to 0 V sub L dt equals, and then this over here, this integral of from negative infinity to 0 of di is really, recall, like 1 di. So what's the integral of 1? It's just I, and it's going from negative infinity to 0. So that means that that's the initial current there. So that's our initial conditions right there. So we get this relationship that I0 equals that, but we also get, for some arbitrary, like if I just put a t here, we would get I of t equals, and then we change the limits of integration over here. So So the I in the inductor equals this integral form right here. So that's where that comes from when we write KCL for this second order circuit right here. So I don't know why the book didn't really summarize it for you, but a few things that you should keep in mind that are pairs, integral and differential forms of things. We had I sub c equals c dv dt. And we can do a similar integration thing like we did right here, and we get v sub c equals 1 over c integral of I sub c dt. So we get that relationship, and the other one that we started off with voltage in the inductor is L di dt, and we can have an integral form of that where we get I in the inductor as a function of time implied is 1 over L 0 to t, or whatever limits of integration that you need, v sub L dt. And these are pairs that come in very useful that we should always remember when we're doing these second order circuits. So continuing on here, I just transferred over. Here's our KCL. So we have an integral and a derivative in there. That's not a real pleasant form to work with. So what we do then is we take the derivative of both sides one more time, d dt of both sides of this equation. Of course, derivative of 0 is still 0, and then we get dv dt 1 over r plus 1 over L v of t. So that's what we get. But that's actually the initial conditions right there, if we have it at time 0. And then this one will be c dv squared, second derivative dt, equals 0. So this is again a second order differential equation. It's actually standard to write it in order of its derivatives, so the standard to write it this way. So plus the 1 over r dv dt and plus 1 over L v, and all of these are functions of t here. So v equals 0. So now we have it in a standard second order form. And V is voltage across the capacitor, but it's also, which is the same as the V in the circuit right there. So standard differential equation, you can assume a solution of this form. This should be looking pretty familiar right now. So as a solution, we need to find an equation for the voltage that solves this differential equation. So we're going to assume a solution of the form a e to the st. We'll substitute it back into this equation, where a is an unknown constant or unknown value and s is an unknown value. We substitute it back into this equation. We did this before on the parallel circuit already, and should be no surprise that we'll get something that looks like this after rearranging some terms also. So because the second derivative of this, we'll put an s squared up front, right? And the first derivative of ae to the st, we'll put an s up in front, multiplier. And there we just put ae to the st in there. So all the e to the st's cancel out, or you divide everything by e to the st, and this is a 0. All the a's cancel out, and you're left with s squared plus 1 over rcs plus 1 over lc equals 0. So this is a quadratic equation where you can find two roots, s1, s2. So here are the roots, S1 and S2, function of R, L, and C, and then we again put it in this form of an alpha and an omega, or an alpha and a beta. The omega naught, the natural frequency, is 1 over the square root of LC, just the same as the series circuit, but I think alpha is a little different. So for the fun of it, this is what the series circuit S1 and S2 had. This is the parallel S1. And this is the alpha for also the series circuit. So they a little bit different just because the coefficients of the differential equation are different, but very, very similar. The natural frequency, interestingly enough, is the same, but the damping part will be different. So this is parallel. This is the parallel case, and this is the series case. Just like in the series case, we have three different conditions to consider on our circuit. One where the roots S1 and S2 are real, so alpha will be greater than omega naught, or the natural frequency. One where the case where the part of the root goes away, the part under the radical goes away, so alpha is the same as the natural frequency, or the case where you get a complex root. So we have the overdamped case where the roots are all real, and our solution will have this form right here. So by substituting back in our assumed solution, we will find out that we'll get a solution of this form. So then there's the critically damped case right before the circuit starts to have oscillatory behavior. The solution will, the two roots are the same value, S1 equals S2, and the form of the solution will look like this. So you can find the alpha right there from values in our circuit. And then the underdamped case, which has oscillatory behavior, you end up with the roots S1 and S2, which, remember, are a function of R, L, and C, will end up being a complex number, where J is the square root of -1. And then the solution will have this form. When you put the solution back into the equation, it will have this form. You know alpha already, and you know the damping frequency omega d here. And in all three of these cases, the coefficients A1 and A2 are determined from initial conditions in the circuit. So let's show you that next. So we need to find the initial conditions. I put here's the original circuit back, and they have the initial conditions shown that there's initially a current I0 through the inductor, and there's an initial charge V0 on the capacitor, and this was our original differential equation, but we are really wanting this to be V at time 0. So we want T to be equals 0, and so this, when we integrate that from -infinity to time T equals 0, that's our I0 amount. And so we have I0, and for the current right here, we know that the initial voltage across this parallel network is V0, so that's V0 over R right here. And then the last thing we have right here is C dV at 0 dt equals 0. Now, since this was a second order differential equation, actually after I take the derivative one more time, it appears as a second order differential equation. We need two initial conditions, and we have two unknowns, A1, A2. Our initial conditions are generally V at some time, and the other one will be dV at some time dt. So these are the two initial conditions that we need to have in order to find our A1 and A2. So from this equation right here, we can just solve for, whoops, that should say dV of 0. That should say dV at 0. No wonder it didn't look right to me. So from these conditions right here, we can say C dV at 0 dt equals minus I0 plus V0 over R. So therefore dV at 0 dt equals -1 over C I0 plus V0 over R. So that's a very easy initial condition to obtain. The other initial condition that we have already, V at time 0, which was just V0. So we have our two initial conditions, and so now it's just a matter of putting together the final solution, finding A1 and A2, which does depend on which case we're looking at with the circuits. Okay, so let's do this example that's in your textbook. So rather than starting at KCL and writing the full differential equation right here, we know enough about this circuit that we can start figuring out some things without going through a formal differential equation solution. So we have that V at time 0 is 5 volts. So this is one of our initial conditions, right? So we need V at 0 is an initial condition for a parallel circuit, and dV at 0 dt is an initial condition for a parallel circuit. So we have one of them already. We have this condition right here that I0 is 0 at time 0. And then we have the values of R, L, and C. So this problem has 3 different cases, so you can imagine one's going to be underdamped, one's going to be critically damped, and one's probably going to be or this one's probably going to be underdamped, and this one's probably going to be overdamped, and one will be critical. So case 1, we'll look at case 1. And so the way to approach this problem is just to say, okay, well, my alpha is 1 over 2 RC, and you put these numbers in, R's and C's, and you will get 26. And then my natural frequency, omega naught, you just put in the formula, which this is the same for whether it's series or parallel, and you put in your numbers and you get 10. So alpha is greater than omega 0 or omega naught, so that we know that this is the case of being overdamped. So since it's overdamped, we know that the solution is going to have, well, we know that the what form the solution will be in, and we also get our roots S1 and S2. Well, we calculate it from our alphas and our omegas, so it's minus alpha, either plus or minus square root of alpha squared minus omega naught squared, and we get our 2 roots. One of them is a minus 2, and one of them is a minus 50. Okay, so those are our 2 roots of the equation, and we've determined that this is an overdamped case, so we know that the solution to the differential equation that describes this circuit will have this form, A1 e to the minus 2t plus A2 e to the minus 50t. So that's our solution. What we have left to do is determine use the initial conditions to determine A1 and A2. So one of the initial conditions that we have is that V at time 0 equals 5. So we say 5 equals A1e, and e to the 0, minus 2 times 0, right? Plus A2 e to the minus 50 times 0. So we get 5 equals, so e to the 0 is 1, A1 plus A2. So that's one of our equations with A1 and A2. We need a second equation, which our second initial condition comes from that derivative equation. So d at V0, which I just did on the previous slide, equals minus, well, you could actually just put it in the equation that I just did on the previous slide, but voltage at time 0 plus Ri at time 0 plus divided by R times C, and so we have the initial voltage here is 5, and the initial current is 0. It's given to us right here. So remember, the tricky part, one of the things that I think is a little confusing in this textbook is that whenever they're referring to I, it's in the inductor here. But okay, so that current was 0, divided by R times C, and you get the value of minus 260. So you put that back in your equation, this equation right here, taking the derivative of it, actually this one, dv dt equals a1 minus 2 e to the minus 2t plus a2 minus 50 e to the minus 50t. T is 0. It's just that we're doing it at the derivative at time 0. So that means these exponential functions will go away. We just found that to be minus 260. So minus 260 equals minus 2a1 plus minus 50a2. So we now have two equations and two unknowns. So you can solve for a1 and a2. And guess I'll have to do a new slide. So when I solve for a1 and a2, I find out that, actually just in your textbooks, two equations and two unknowns, I get the value of a1 and a2, and I get the final solution for what v of t is minus 0.2083 e to the minus 2t plus 5.208 e to the minus 50t. So I can plot that voltage as a function of time, and you'll get some kind of, I think this one has a negative going one because of the direction of the current flow, but you'll get some kind of a function that looks like that, which I can plot it in MATLAB and show you. So now case 2 for this problem, as you can imagine, will be the critically damped case. It's when R equals 5 ohms. So you're actually going to go through the same process again. Omega naught will still be the same. It'll still be 10. But since you'll find out that omega and alpha are both 10, so we will have critically damped. Remember, these are computed from R's and C's, but you'll find out that they're both equal. And now our solution will have this form because we're critically damped. And there will only be one root, which you will have computed from the equation, and then that will be the form of it. And again, you do the exact same initial condition kind of process, and with your two initial conditions, and solve for a1 and a2, and you get the roots. Case 3 will be underdamped case, and again you're just going to go through, calculate the values from here, alpha and omega. You'll find out that it's a underdamped case. You'll have complex roots. You'll have a form of the equation that has signs. The solution will have sines and cosines in it. You will again use the same formulas for initial conditions, find a1 and a2, and get the final equation for v. So one more example of the natural response of a circuit, which is this one. The only thing really different about this problem versus the ones that we just did for a parallel circuit is that the initial conditions aren't being given to you in the circuit. You have to find them from what happened at this circuit before t equals 0 and this switch closes. So that's really kind of the only difference in this problem. But it's still, I think, worthwhile for us to look at it, because you have to be able to figure out initial conditions, and sometimes that's difficult for people. So here we are. So what happens before t equals 0 is what you have to look at. T equals 0, the switch closes. Before t equals 0, so a long time has happened before then, what happens is this capacitor should be an open circuit by that time, and it should be fully charged. What else happens at infinite time before t equals 0? The inductor will be a short at that point. So for t less than 0, just before the switch closes, and actually it's minus infinity to 0 time. We have the circuit now that looks like this, minus plus, I'm supposed to say minus 40 volts. And we have 3 ohms here, 30 ohms, sorry. And the inductor is a short. The switch is open, so nothing is happening right here. And we have this resistor right here, this 50 ohm resistor. And the capacitor is an open right now because infinite time has gone by, which means no current is flowing in there. And so that's what the circuit looks like before you close the switch and make things happen. So from this we can find out what our initial conditions are. So I0 would be, see, I'm going to make my current go this way. I0 is the current in the inductor, with the inductor is now shorted out, or it's a short right now because infinite time has gone by. And V0 would be the voltage that's across this 50 ohm resistor, which would be the same as the voltage that's across that capacitor. So I0 we can get just by virtue of, we see a simple little series loop right here, so it would be 40 volts divided by, 40 volts divided by the total resistance, which is 30 plus 50 ohms, so 40 divided by 80. So the initial current, I0, is 0.5 amp. And looks like the circuit defined it in the other direction, so I at time 0, which is in the inductor, is negative 0.5 amp. Only because of the way they defined it versus our conventional current flow of leaving here. This is actually going to be the true case because when we do the natural response next, we'll see in a moment that we'll be finding a natural response of a parallel RLC circuit without a source being present, and then this capacitor is now in a discharge mode at that time. So V0, which is the voltage right here, the initial charge there, V0 is actually the voltage on the capacitor at time 0 after infinity time has gone by. In this situation is going to be I times 50 ohms because that's the voltage that's right there, and so you will get 25 volts. So that was not too bad so far. And then we find that in that. So the other initial condition that we will probably need, because we have a second order differential equation. Well, before we do that, let's look at what the circuit looks like now when the switch closes. So when the switch closes, there's a short right here, and so that's like joining this node and this node right here. And this part of the circuit is really no longer connected to the other part of the circuit. So what you really have when that switch closes, well, it didn't draw it very well, is you have that part of the circuit right here because you've shorted out these two things by shorting it. And then you have completely unrelated this inductor in the circuit here, and the 50 ohms and the capacitor right here. But these two circuits are unrelated to each other. It's like you just shorted this guy out, so it's behaving independently. No current from this circuit is going to go into this circuit because this circuit presents some resistance. And over here, this is a short, right? So this part of the circuit has no relation now to this part of the circuit. And that's really, I think, the key to doing this problem right here. So now we only have this circuit to consider, which is an inductor, a resistor, and a capacitor. And if I move that inductor around the corner, we have our standard parallel RLC circuit, and we're looking at its natural response from there. So let's find our other. Now this is the circuit, and we have to find the dV at 0, dt, dV at 0, dt initial conditions, and we know without having to rederive it every single time, which I'm prone to doing, that it will be the initial voltage plus R times initial current in the inductor, initial voltage across the capacitor, initial initial current in the inductor divided by RC. So we can do that. The initial voltage we found in the capacitor right there is 25 volts. And the initial current in the inductor over here. Yes, because initially there's no, remember there's no initial current over here because this is an open circuit. So all you have to consider right now is the inductor and the resistor right there. So the current that's in the resistor is the current that's in the inductor, and that makes sense. So so it will be plus R. I is, by our convention, 0.5 amps. So this is a place, and we have R. This is a place where careful accounting of your signs becomes very important. Divided by R times C. So this divided by 50 times 20 times 10 to the minus 6 because it's 20 microfarads. So then we get this other initial condition, and it turns out that when you do that algebra right there, that math right there, you will get 0. So now the rest is pretty much calculations and putting it into the correct form. So the hard part of the problem is over, was recognizing where to get your initial conditions. So we calculate what alpha is just by putting in the numbers. We get 500. We calculate what omega naught is, and we calculate our two roots, S1 and S2. So S1 turns out to be this number, S2 turns out to be that number, and we say alpha, alpha is greater than omega naught, so there we have an overdamped response. Therefore the solution is of this form right here. All we have left now to do is find the roots A1 and A2. I mean, not roots, the coefficients A1 and A2, which we find from the initial conditions. So we just found the initial conditions on the previous slide. Because V0 was 25 volts, that means we put T equals 0 in this equation. 25 volts equals that. So we get this equation of A1 and A2. Then we found the derivative of V0, and we found out that that was equal to 0. So we take the derivative of this equation, set T equal to 0, and that will result in this equation. So we have two equations, two unknowns. We can solve for A1 and A2. This is an interesting response because two different signs. But it will still be an overdamped situation, and we get the final solution, which is a nice function that we can plot as a function of time.